Let's go ahead and get started as you all flow in. It's good to see everybody this morning, 3/4 or more of the way through the week. And I hope you're all having a great time and interacting well. Just a reminder, the code of conduct, I think it's been going good. I don't think I need to go through the details, but it is always a good reminder at the start of the day to recall that we are all here to collaborate and to treat each other with respect. It's Ian again. Is it me?
No. We had already turned it on.
Seemed like I did the talk yesterday or Monday from here.
That was a different problem.
Okay. Okay, hopefully online you're seeing a code of conduct reminder slide. There we go. It's going. Okay, and also just a reminder that this session is not just recorded, but it's online. And if you are online, we will be monitoring the chat channel for questions when we get to that point of the morning. And of course, all of the regular expectations for remote participation and muting and all those things, I think are automatic, but if they aren't, your behavior would be, appropriate behavior would be appreciated. Okay. There we go. So I have the lovely opportunity, this is not the right slide. I'm going to introduce Aaron while he finds the right slide. Here, you stand there. I'll stand here. So our first speaker this morning is going to be Aaron Roodman, who joined SLAC in 1998. And I stole one little sentence from your bio, and it says, spent 20 years wondering what happened to all the antimatter in the universe and switched to exploring why most of the universe isn't matter at all. The first time I read it is, doesn't matter at all, but okay. That was just me. Worked on Babar, worked on the PEP2B factory, did a lot of hands-on work on DECAM, participated in DES, and currently, and I had to write all these down, is the professor of particle physics and astrophysics at SLAC, is a deputy director for Roodman Construction, is the LSST Cam program lead at SLAC, and is the interim FPD co-director. Deputy that's just a lot of terms, and I don't think deputy in there matters. It's all very important, and it sounds like you're very busy, but with that, I really do want to introduce you or have you come on up and tell us about the actual progress with the camera, which we're all desperately waiting for.
Okay, yeah, it really is my pleasure to give this talk and discuss the progress with the camera, its status, and a little bit about its performance. So, for many years, we looked at engineering drawings, CAD drawings like this one, and so it is very gratifying now to be able to see the camera in its basically completed form. So the camera has been assembled. The last thing that we had to do of installing glass filters happened a couple weeks ago, and we're in the final testing phase. So I want to use this time, actually maybe to look back a little, and as I describe how we put the camera together and what maybe one or two of the challenges were, mention again why the camera ended up the way it did. Why did we design the LSST camera in this way? I gave a similar and longer talk at the Dark Energy Science Collaboration's Dark Energy School a couple weeks ago, and that has active learning as one of its goals. So I'm going to use a little element of that and maybe force you to look up from your laptops and talk to your neighbor for a minute. So I hope you'll participate in that piece. Then I'm going to show some performance highlights of some of the results from the laboratory testing that we've been doing. Okay, so let's take 30 seconds, talk to your neighbor, and see if you can understand why do we have 3 lenses in the LSST camera. 30 seconds. Talk to your neighbor. Oh, thank you. Okay. All right, I'm gonna interrupt those good conversations. I know 30 seconds isn't enough, I guess. Excellent. That's great. Okay. So why do we have 3 lenses? So obviously the CCDs have to be cooled. We operate at the pretty typical temperature of minus 100 C. That's to avoid dark current, hot defects, and the like. Obviously, you've got to be in vacuum at that temperature, and if you're in vacuum, you need a window. But once we have one refractive element, stepping back, we have a 3-mirror system, right? 3-mirror system should be enough if you were okay with a non-flat focal plane and you didn't have to cool the CCDs. But once you have one lens, you need at least one more to make chromatic corrections. So in the dark energy school, because it was more students, so give and take. So you just have to feel good if you knew the right answer, and if not, maybe you learned something. Okay, so let's look at them. The top left there is the L1. That lens is listed in the Guinness Book of World Records. It's the largest lens ever built for astronomy at 1.55 meters across. It is in the paper copy of the 2021 book. I think right now it's just online. Below that, you see L2. They're in a package together with carbon fiber on the outside to absorb stray light. The upper right is L3. That's the vacuum window. It is an optic. And then in the bottom are the 6 filters in their storage box. Okay, next question. Why 3.2 gigapixels? And sort of a related question, why do we have a plate scale of 0.2 arc seconds per pixel and 10 micron pixels? So again, 30 seconds, talk to your neighbor. Okay. I'm gonna interrupt. I hope that generated some more thoughts. So the overwhelming design goal, to meet the science goals of the project, is to have a 10 square degree field of view. And for surveying, of course, we've wanted to maximize our étendue. We have our 8.4 meter primary mirror, and 10 square degrees will give us the science that we want. 10 square degrees, then how many pixels you need depends on how big the pixels are in the sky. The very best seeing or image quality that I think we can imagine, if there's almost no seeing effect, is around 0.4 arc seconds. It is possible, actually, we could do a little bit better. But our estimates are that's the very best we would do. And of course, we want to sample that well. So 0.2 arc seconds per pixel is a reasonable choice. And of course, for CCD technology, deep depletion CCDs that are thick for good red response, 10 micron pixels is a reasonable choice. So it's all optimized together. And on the right is one of our images of the full focal plane, just after we finish the assembly. Okay, there's only one more question. And this is more of a little bit more detailed in the design. But this is one of the features that really drove a lot of the camera design. So the question is, why do we have the CCD controllers and the digitizers inside the cryostat? So 30 seconds. Oh, maybe that's harder. Okay, I'm gonna interrupt one more time. So this one is a little more involved, the explanation. So, and I'll say actually I was not even part of the project when this decision was made. I think it was in 2006, 2007. I only started working on the camera in early 2011. Right, part of the design, and maybe it's changed now with the current ideas about the way the survey strategy will work, but was to have one image in every available direction in 3 or 4 nights. And if you do that, that leads you to 30-second exposure times. We have, the nominal is still 15 plus 15 second, although that's under active discussion. And if you do that, you want to minimize the dead time. You want to spend as much of your time on sky and not reading out the focal plane. So 2-second readout looked achievable, and that gave a reasonably small amount of dead time. So to get 2-second readout, what do? We decided to push to 0.5 megahertz pixel read rate. That's actually pretty fast, but it looked achievable. But to get 2-second readout then, with 0.5 megahertz, you need to have amplifiers, each amplifier section that's only 1 million pixels. You don't want CCDs with just 1 million pixels, it's not enough. 4K by 4K looked like a good size, and if you have 4K by 4K, you need 16 amplifier sections. That is, right, so that required custom CCDs. No one had done that before. Two is quite typical, not 16. But then with 16 amplifier sections, 189 science CCDs, plus 12 for guiding and wavefront. Multiply that up, that's over 3,200 analog signals. And pulling 3,200 analog signals out of vacuum on cables looked daunting, while staying within our read noise, crosstalk, and other requirements. So the decision was made to put the electronics as close as possible to the CCDs, and that's why it's in vacuum. So that drove a lot of the other design features. Okay, that was the last question. Now let's show some pictures. On the left is a flat field. I think this is sort of G-band flat field from our in-lab testing. The gain matching isn't perfect, so you can see the amplifier sections. One of them is circled. In the middle is the raft. So that's the sub-assembly with 9 CCDs and 3 electronics boards that you can see at the top. And those are the controllers. And then on the right is the back of the cryostat, where you can see the grid where the rafts fit before they were installed. It's a very, very compact package. But it has yielded roughly 2-second readout successfully. Now, what about the 3.2 gigapixel focal plane? Oh, that's in the Guinness Book of World Records too. The reason is our communications put out a press release that we had finished the focal plane and said it's the world's largest focal plane. And the Guinness people contacted them and said, hey, can you prove that? And we were like, well, okay, here's what we think. They went off and did their research and came back and said, yeah, you belong in the book. So on the left is one of the CCDs. Below that is the sub-assembly with 9 CCDs. Then the raft, that's the same picture I showed, is a very tightly integrated package. And on the right is, that's Hannah Pollock and Travis Lang working to install the last raft. That happened just before the pandemic. One of the many challenges in that are the tight tolerances. Very tight to minimize the amount of unused area on our big focal plane. And so the gaps are roughly 0.5 millimeter between adjacent CCDs, either in one raft or adjacent ones. You can see how close the two come. And in all of review talks, Kevin Reel always showed this as trying to park one Maserati in between 2 other Maseratis with kind of a centimeter clearance. It's about right. Okay, so That's the focal plane. Now, I said I would mention challenges. Maybe I'll just mention one, and I think this is something that's definitely had an impact on our schedule. It's been one of the challenges we faced in the final assembly and getting ready to send to Chile, and that is the refrigeration systems. We have two inside the cryostat. One cools the CCDs to the -100 C I mentioned. The other cools the electronics. It's about a kilowatt for the electronics at -40 C. The focal plane is up to 500 watts at -130 is what the thermal ballast is at. I've got that same picture of the raft showing you where the different temperatures go. The CCDs are at -100. The arrow shows where the -130 plate is attached. The -40 is where the cold plate is attached, and then the electronics is a little bit hotter. So if that doesn't all make sense instantly, that's okay. Just take away that it's two thermal systems mechanically interleaved. The cryo system is actually the difficult system. I think at one of these keynotes, I don't know, 6 or 7 years ago, Rafe Schindler gave a really nice talk describing the technology brought to bear on the cryo system. The cold system was quite conventional vapor compression system. Not so different than what you would build for a biological refrigerator at -40 C. It worked well in subsystem testing, but in the final testing, we had serious problems. And it would work and then lose its cooling capacity. So it's a long saga with a lot of work by the camera team and others. But in the end, we moved to a new system, which we call the pumped coolant system. So that will have a chiller. All of the chiller and compressors are located under the primary mirror, and in this case, the chiller will pump fluid at -50 C up to the camera. So it's an even simpler system, but it did require us to develop vacuum jacketed lines, and we have designs are in the middle of building the new wraps to accommodate those bigger lines. So that has been one of the big things that we've had to deal with in the assembly of the camera. The bottom plot is from our camera telemetry, and it shows the temperature of the -40 C plate from initial cool down and then operation over a couple weeks in June. So not totally without problems, but actually look pretty good. So we're confident that we're going to be good with this new system. So I notice often in these sort of talks, people just talk about all the successes. I think it's actually interesting, useful to describe a little bit some of the challenges. This was not the only one, I have to say. Okay, maybe some more pictures. So here's some snaps of the camera assembly. From the top, you see the beginning of the raft installation, then moving the cryostat with the utility trunk. That's got all the support electronics, vacuum, refrigeration system behind the cryostat. Then you see us craning in that package into the camera body. On the right, you see the focal plane. You can see the two beautiful colors in reflection. They're two colors because we have two manufacturers of CCDs, and they have slightly different quantum efficiency, especially on the blue edge. And when you look at them, you're seeing one minus the quantum efficiency, and you see the difference in colors. Then there's a nice picture. I think that's Travis again. You can also see some of the metal bars are part of the filter exchange system. That's the carousel that rotates the filters into place before they're grabbed. I have a video of that in a sec to show as well. Then the next one is the shutter being installed. After that, you see the L1, L2 installed. You can see the hexapod that connects it to the camera body. And then at the bottom is a photograph of the assembly most of the way through, kind of with a different view. Here's one of the pictures we really like, looking down the barrel. And then I do have one movie just to show you both the shutter and the filter exchange system in operation. Okay, we have to. No problem. So the different colors are because the anti-reflect. Oh, that. Oh, Jesus. God. Don't distract me, Robert. So, so this is a video taken recently. It shows the shutter opened. We'll see the shutter close at the end. So the filter exchange mechanism moved up. Now it's grabbing one of the filters. It's going to grab the R-band filter. And then in a second, it's going to make its way down. And it goes into place a little bit slowly to get it placed just right. And then you can see it. So it's the R-band. I could have asked this question too, but it looks blue in reflection. You're seeing it primarily in reflection where it looks blue. And there it's basically in place. So, and I think if we wait, the shutter closes. So we have 3 of the glass filters in place. We have another filter with pinholes to use for some testing. Okay, maybe we'll go back to the slides. Okay. So we're just about ready for the sort of the final testing period, and then we'll be able to ship it to Chile. I think I'm doing okay in time. Let me describe actually some of the results that we've had with our program of laboratory testing. So first, what are the drivers? What are some of the drivers for image quality? The requirement for the camera, sort of the camera extra contribution to image quality is 0.3 arc seconds, full width. That's dominated by diffusion. And the diffusion, once you pick a voltage for the back bias, we use 50 volts almost everywhere. There's 3 CCDs that are at 30 volts. But 50 volts gives you a little bit under 0.2 arc seconds, full width. And all the other contributions are subleading. One of the other ones is due to the non-flatness of the focal plane. So we worked very hard, as did the CCD manufacturers, to yield a flat focal plane. There's no adjustment, sort of done dead reckoned, but with really solid control of every component that's stacked up, we got the focal plane height shown here. So the left is a map. This was work by Andy Rasmussen that shows the height. The color scale goes from about plus or minus 15 microns. And if you tally it up, you get a distribution that ends up being kind of Gaussian with an RMS of just over 4 microns. So that will keep the contribution from flatness to about 0.05 arc seconds, so well within our required level. That looks great. I think there was discussion of active optics. We should be able to see this pattern if we have the full focal plane out of focus in a donut pattern. So it'll be nice to compare. That looks good. What about electro-optical testing? So right now we have 2 different light sources. Both of these were developed from hardware built by the Grenoble group, CCOB we call them. The wide beam was modified by my student Theo Schutt to work in this configuration. It illuminates every pixel. It's sort of flat. It's flat to 15%, which is fine for our purposes. And this is one flat field or flat-ish field taken with the I-band LED. It's been gain corrected, but not QE corrected. And in fact, this orientation is rotated from the color pictures I showed. But if you look at the CCDs that look a little bit out of family, those show up in reflection. They match actually quite well. We also have what we call the CCOB narrow beam. That's a pencil beam, wavelength selectable on a movable stage so we can point it where we want. We'll use that for throughput testing. We'll also use it to get an independent measurement of the optical alignment, sort of an independent check. And for that, we'll blast that beam in one spot and then look for all the reflections. And so the primary spot is shown, and there's about 18 reflections. I've got the arrow pointing to a few of them, and those are all double bounces off the CCDs, one of the optics, and back, or between 2 of the optical surfaces. And that's being studied to make sure we understand that pattern. It's kind of an interesting test. This has no filter. This had no filter. We're going to do this probably without filters. The filter alignment is a different story. Okay, maybe some other results. So we have a suite of basically calibration images, not too different than the calibration images we'll take in DOME. And then those get analyzed by CP pipe, it's called, the calibration pipeline, plus for these plots, an additional pipeline called EO pipe that Jim Chang developed. All these images are at the USDF. We have about 40,000 images we took a year and a half ago, and then in a couple of weeks we took another 4,000 images in June, with more to come. We can study all sort of the basic quantities per amplifier. So on the left is read noise. Most of the CCDs meet the original requirement, and we've analyzed carefully the few CCDs that have slightly higher read noise, which will have minimal impact on our science. On the right is shown the gain from a photon transfer curve. You can see that there is a difference in gain between the two manufacturers, but those look quite regular. And I can say there's a few that are, amplifiers that are non-functional or have issues. That's at the level of 5 over the 3200. We could also look at full well. That looks pretty good. There are a few CCDs that have somewhat lower full well. We've been actually working to characterize the different effects that happen at the full well. There isn't a single full well. Depending on what you care about, it happens at slightly different points. We'll be characterizing that. And on the right is a dark image. This was taken with the shutter open, but the room light's off. There's clearly still some small light leak or light source. We actually don't know what it is yet. We spent a little bit of time on this, maybe not enough, but the level is extremely small. The color scale goes up to 0.01 electrons per second, so tiny. There are also, if you look closer at this, there's some other interesting features. There's some issues with the bias stability for a few channels. That's something that's occupied a lot of our time and effort studying, characterizing, and figuring out how to fix. But overall, the focal plane looks extremely good. Some other studies. So there's a paper that just came out. Johnny Estevez, a student from Michigan, is the first author in this with Yosuke Itsumi and a bunch of other people from the camera team. This looked at basically artificial star flats. So we had, in our testing a year and a half ago, we had a grid of stars that we could raster. So effectively we could, with kind of at the level of 1 million stars, do the same thing you would do with a star flat on sky. So we studied basically photometry, astrometry, and shapes. And these plots show the tree ring pattern, basically from astrometry. We see the pattern we expected on shapes, and as well as the PSF size. There are patterns on the blue edge in all the CCDs due to the surface treatment, and one of the things we were most interested in was to check that that was strictly a quantum efficiency effect and not a pixel size effect. And one of the conclusions of this paper is that those effects are just quantum efficiency. So they'll still have to get dealt with. I don't know where Eli is. That'll be one of his challenges. There he is, to deal with those variations, but at least they're not pixel size. They won't affect astrometry or shapes. Anyway, that just got put on the archive. Just some other vignettes. We have detailed studies of crosstalk. I think Tony, someone in Tony's group had a poster on some crosstalk measurements made at UC Davis that really went into fine detail with one CCD. We have data from all the CCDs, all the amplifiers with the crosstalk level. You know, one of the nice features, and this is something that came out from having the electronics so close to the CCDs, crosstalk is actually quite small. So the nearest neighbor crosstalk is kind of 2 × 10⁻⁴, and it drops off as you move away. So in this image on the left, we had 4 really bright spots, and then you can see the other crosstalk spots. This image also shows another effect. There is a little bit of persistence if you go above full well. We're still working to characterize that, and I think that's an open question for data management and the pipelines, how and what kind of correction that might need. Another interesting effect is in charge transfer inefficiency. Some of the CCDs have a pocket at the serial, at the end of the serial register, and that gives you significant amount of charge transfer inefficiency in the serial direction, but it's all at one place. It doesn't vary across the detector, and that one looks to be totally correctable. This is one of the monitoring plots of that, and there's a paper that Adam Snyder wrote as part of his thesis. And there's a correction algorithm that has been implemented in DM to take this effect out. Okay, I think I'll be able to leave some time for questions too. One other thing that people always ask is, how are we getting to Chile? And the answer is very carefully, but we're actually going to ship the camera in its current configuration in one piece. We will take the filters out, and we'll go by chartered 747. So we'll actually have the whole plane to ourselves, and we will fill it with the camera, as well as all the support and test equipment will also go. So one more engineering drawing, because we haven't put the camera in its frame, but that frame exists, and we've actually tested it. The image on the right, and Kevin would have to tell me who that is. I don't recognize Freddie. Okay, so this is a sort of fake our camera surrogate, sheet metal and dumbbells, placed on the frame in the shipping crate, and we sent it, not by chartered plane, but by plane to Chile, and this is it being received on level 3. And that test was quite successful. We demonstrated that the frame did its job in damping out oscillations or any shocks along the way, and it was actually a more rigorous test because they drove across country, not to SFO, and the plane even stopped somewhere that we didn't know it was going to stop. But that was a successful test. So that is how we're going to send the camera to Pachon. Okay. So obviously, a complicated, challenging instrument like this is the work of many. Obviously, Steve Kahn led the camera project for many years, as well as a big team of people from SLAC, from Brookhaven, from IN2P3, Davis, and a couple other places. So this is a montage we made once we finished the focal plane to get everyone in the picture. And these are on the right is the institutions that were involved. So with that, I think I will stop and take questions. Yeah, we should go to the mic.
Thank you for the nice talk. I'm Satoshi Miyazaki from Subaru. I'm wondering why you cooled your electronics down to -40. Your electronics inside the viewer has to be cooled down. Why do you do so?
As opposed to room temperature?
Right.
Well, so we certainly have to cool them some, given the amount of heat that's being produced. So the question is what temperature to operate at. And,
no. Why do you have to cool it down? Or it is cooled down passively, or?
Well, let's see, it's in vacuum, right? So passive cooling, it would go up to 50 or 60 C if we didn't do anything.
Right.
So, which we judge to be bad for the longevity of that electronics. So I think the biggest factor was for lifetime and operation. That operating cold is better.
And sorry, just a quick note. The electronics themselves are not at -40. The cold plate's at -40. The electronics are much warmer.
Oh,
well, so we actually have, each board has 10 temperature sensors, and the temperature ranges from -20, but right on the FPGA, it's probably closer to 0.
I see.
But
because if you don't have to cool the electronics down, your heat load is much, much smaller, right? So that's why I'm asking.
Well, I mean, it's a kilowatt in the electronics total. So,
But
the other thing is that the other factor, which is also important, and maybe was an equal driver factor, is that you can see it, right? The thermal zones are interleaved, okay? So, let's see, maybe I have a mouse. So here's the board, but the boards go all the way through this crate. So we call this box the crate. The cryoplate, the thermal ballast for the CCDs attaches here. That's at minus 130. So the heat from the CCDs is taken out through this nickel-plated copper box, which surrounds the electronics. So the other factor that's critical is that, so you have basically electronics at minus 10 or minus 20 inside the box that's at minus 30 to minus 100. So the heat load between the two is critical and, was part of the equation. So if you operated the electronics hotter, you would not be able to get the CCDs cold, with this setup. So that is also an important consideration, the fact that these two thermal zones are physically intermixed in this way.
Okay, maybe I should understand more about your thermal design.
Yeah.
But you only have to cool the CCD down, right? And any other point can be like minus 10 or 0 in order to make your electronics life longer rather than operating at minus 50 degrees. But
right.
So
I mean,
the
ballast is at minus 40, but
it's balanced, yes.
yeah. I mean, okay. As I say, the electronics is roughly minus 10 to minus 20, and I think if you're right on the FPGA, it's warmer still.
But I was wondering why you can't make a thermal insulation between CCD and electronics.
Okay. That maybe we need to sit down and
okay.
look at it with pen and paper.
All right, thank you.
Thanks, Satoshi.
Very quickly, how much of the stage you're on would the camera take up?
Say it again.
How much of the stage that you are on would the camera take up?
Oh, so how big is it, right? So the lens, I'm a little over 6 feet, so the lenses come up to about here, 5.5 feet, and the distance from the front to the back of the cryostat is around 2 meters.
You can put Victor on the other side of the camera.
I don't know, it's big. It's wide. Yeah, so the lens is there, the cryostat's going to be about here, the back of the utility.
Great, thank you.
It's also very disconcerting to stand in front of it because you cannot see where the L1 is. Obviously, it curves out. I find it slightly freaky to stand there. Yeah.
Yeah. Hi, Cesar Briceño, NOIRLab. I had a question about your one of the first images that you showed. There's some kind of banding across the device. Before that, yeah, go back. I think further back.
This one.
Yeah, what's the banding?
Okay.
Across that?
So. Yeah, so the question is, what's this structure on the left-hand side? So this is an E2V sensor. I think this probably is G-band. It's probably not U. It's even worse than U. And so that is an annealing pattern from the passivation done to the CCD surface. After it's been thinned, and so that annealing leaves a remnant in the quantum efficiency. And so it could be U. I think this is actually G. The effect is mostly gone by R band, but this is a quantum efficiency. It will come out as a quantum efficiency effect, but it's due to the annealing that the manufacturer did. There is a different pattern in the ITL sensors. Those have a different method for passivation. And many of them look quite smooth, but some of them have, quite a remarkable looking feature basically in the anti-reflective coating or in the surface properties that again you see in U and G band. Our name inside the camera for that is coffee stains. It looks a little bit like if you spilled coffee. Both of them are going to be, they're known issues. We've known about those basically since the start, and they should come out in flat fielding. Although it's second order, I think there'll definitely be some work that Eli and the calibration team will have to do to deal with that.
We have one final question from SLAC. How complicated is normal maintenance of filters, shutter, snow, etc. once the camera is on the telescope?
Yeah.
How much of the camera needs to be disassembled if there's a problem?
Excellent question. So start with the filters. So I'm going to assume that's about the mechanisms, right? So those are the moving parts where you definitely would worry about their long-term operation. So the filter exchange system is made of two parts. There's a carousel that moves the filters. That is not replaceable. That is built into the camera body. But the exchanger, the piece on cams that grabs the filter, brings it into place, that is a separate assembly. And it can be removed with the camera on the telescope kind of through a hole in the top. So it can be craned out. And there are two of them. So we have, the second one is still in France, going through its final checkout, but we have two. And the notion is that on roughly a yearly timescale, you would swap them, and do maintenance on the unit that you pulled out. The same is true of the shutter. We have two shutters, and the shutter is also removable on the telescope. It's actually kind of hard because the shutter is pretty big. So you have to take out the filter exchange mechanism first, and then you can take out the shutter. You have to snake it through the legs that hold up the L1, L2. And that takes multiple motions. So there's actually a special 5-axis gantry that attaches to the side of the camera and attaches to the shutter and does the roughly 15 movements that you need to snake it out. And that has been tested on the camera at SLAC, but that's how we'll take out the shutter. And so both of those are maintainable in that way. Okay, good. All right, thanks for your attention.
Thank you, Aaron. Okay, let me introduce Dr. Dara Norman. Dara is an astronomer at NOIRLab, has been for since the year 2000 when she joined Aura. She is the Deputy Director for the Community Science and Data Center, CSDC, at NOIRLab, is the Head of Research and Inclusion, or Research Inclusion, for the initiative for EUSELT, and is the President-elect for AAS, which is a And so I want to welcome Dara and appreciate you coming out.
Thank you, Victor, for that introduction. I'm really happy to be here, and I'm excited to talk to you all about supporting scientific excellence and those who animate it. I am Dara Norman, and I am at NOIRLab, but for all my talks, I say that all of the comments and the opinions, people who know me know I'm very opinionated, expressed here are my own and are not necessarily those of my employer or of the Roodman Observatory. And so to get started, I just want to remind us all why we're here. I grabbed this image off of the Roodman website, and it just reminds us that what we're waiting for is, a telescope to be done, and we're going to get great data. And whether you're in one of these science collaborations or you're not even in a science collaboration, we're all waiting for the opportunity to do the great science that we've been hearing about at this meeting. And so I want to take a little bit of a step back and talk about, how we got here. And we got here basically because the community thought that this was a project worth doing. And the way that we come upon these projects that we feel like are worth doing is through these decadal survey documents that the community gets together on a 10-year cycle and decides what are going to be the real scientific challenges and what tools do we need to answer the questions and the goals that we have for our science. And so there have only been 7 decadal surveys, the first one being in 1964. Each of these decadal surveys is its own little snowflake, but we, and of course the Roodman Observatory, back when it was LSST, was a top recommendation of one of these decadal surveys. But the most recent decadal survey has actually been pretty groundbreaking in how it has addressed issues of workforce and data access in our community. And so this one that's a little bigger is the most recent decadal survey. And while it has been groundbreaking in talking about what our workforce should be like and how we should proceed with our workforce, it is not unique. Every one of these decadal surveys actually has addressed issues of the workforce, including the very first one, which talked about why we needed national observatories in the first place. So the one thing that is groundbreaking about Pathways is really the fact that it really talked in clear terms that people are what is needed to make this science happen. And we need all kinds of people. Aaron showed, all of the teams that were working on the camera from in his last slides. But we need all kinds of people. We need not just the scientists, but people who do the observing, the people who build instruments, who build the telescope, people who design things, the people who test things. And we need students, right? We want to make sure that our scientific goals continue forward. So Pathways was really instrumental in pointing this out, that the people who make up the profession are the most fundamental component of the research enterprise. And that to fully utilize the broadest range of human talent is something that we need to do, with a strong emphasis on broadening access, removing barriers to participation, and creating environments that are free of harassment and discrimination. And I added a recommendation from the decadal survey that there should be targeted programs to improve diversity at each level and improve diversity on project teams, participants, and for beneficiaries of our science. So why do we need to build inclusion, diversity, equity, and access into our research programs? Well, from my point of view, there are the moral reasons and the practical reasons. The moral reasons boil down to if we really believe that the intelligence, the ability, the drive to do science, to do physics, to do astronomy are distributed amongst the population without regard to race, gender, or a socioeconomic background, then if we don't see those populations represented in our community, there's some access issue. There are some biases. I heard recently someone say, ability is everywhere, but access is not everywhere, right? And there are also the practical reasons why we would want to include diversity and equity and access in our research programs, and that's that a diverse workforce really does lead to better outcomes for science, and by not actively promoting these issues of inclusion, diversity, equity, and access, we're going to lose talent. And that means that there are going to be some discoveries that will be left on the table, that maybe take longer to get made, and maybe don't ever get made at all. And so I am of the mind that whatever brings you to the idea that we need diversity, inclusion, equity, and access in our research programs, that's okay with me. I don't think one of these reasons is better or worse than any other reason, but I do think that we need to continue on this path. I also want to talk about the idea of equity. Equity and equality are not the same things. Equality is the state of being equal, whereas equity is actually a focus on outcomes. It's a focus on trying to provide people with what they need to reach and exceed their goals. And as we put policies and practices into place to promote inclusion, diversity, equity, and access, we need to keep this difference in mind, because it's gonna, just making things equal is not necessarily going to lead to the best outcomes. I also wanna point out that all policies and practices, no matter what they are, no matter what ones you put in place, they're gonna come with pros and they're gonna come with cons. And many of them are gonna come with unintentional consequences that you didn't even think of. And I'm not picking on these particular policies, they're just policies that, are relevant in our field right now. But one way that we can mitigate any of the cons or unintentional consequences that come from these policies is to do an assessment, to really evaluate the policies after they put in place and see if they really are supporting our inclusion, diversity, equity, and access goals. And if they're not, then we should look at how to revise and move forward maybe on a different path. But I think we're really ready to embrace this idea of inclusion, diversity, equity, and accessibility in our research programs. And the rest of this talk is gonna be about why I think we're ready. But back in 2015, a number of us got together and implemented the Inclusive Astronomy Conference, which brought up a lot of these issues, and I think directly led to the kinds of wording that we see in this Pathways Decadal Survey. And I stole the title of this talk actually from a quote in the Decadal Survey, that the pursuit of science and scientific excellence is inseparable from the humans who animate it. And so I think we're starting to see the results of inclusive astronomy play out in the wider community. So why am I so optimistic? I'm going to talk now more about the things that I'm seeing happening both in the community generally, but specifically within Roodman for what makes me think we're ready to do this. And in particular, back after inclusive astronomy, a few of us were invited to speak to Obama's President's Council on Science and Technology. And I brought up 3 areas that I thought were going to be important for us to really move forward on cultural change in astronomy and astrophysics. And those were leadership, that we needed to see leaders step up and take seriously this idea of inclusion, diversity, equity, and access in research programs, that we needed incentives that made research funding tied to metrics on progress for underrepresented groups, and finally, that we don't know what we don't know, and if we don't ask the people who are actually experiencing the barriers and the biases, then we won't really understand how we can fix them. And so what I'm seeing is actually leadership opportunities stepping up on providing incentives for that kind of work on inclusion. And at this meeting, talks by Kathy Turner and Ed Ajar and Luca Rizzi actually highlighted some of the ways in which the DOE and NSF are implementing some of these incentives for people to write proposals that take into account the kinds of things that they're doing to promote diversity and inclusion in their in their collaborations. Also, NASA has been stepping up in this area. NASA has made inclusion one of the 5 mission success pillars for the agency. And I'm going to talk a lot more, actually, about these inclusion programs, or inclusion plans that NASA, both NASA and DOE now have implemented. I also want to talk about how I've seen this, why I'm optimistic about this for Roodman. And many of you may have seen my plenary talk at the AAS in 2020, remember 2020? And I presented this little anecdote where I envisioned and I mentioned a big astronomy project that I had been involved in since its early days that really had cutting-edge technology. It had all the things, right? Cutting-edge technology, innovative methods that would lead to great science and opening up new areas of science. It also really had incorporated a community collaboration in a big way, and the project really valued education and public outreach. And in fact, the program at that time that I was early on, it had a broadening participation program that was really a model for improving pipeline building by partnering with professors at historically Black colleges and universities and their students in small research groups to be partnered with people who are on staff of the big astronomy project. And that broadening participation element was actually modeled on a very successful program in another agency. However, 10 years in, what I had noticed at the time was that while all those other great things that the big astronomy project had were still around, what was missing was that broadening participation element, and it just wasn't there as part of what you were seeing when you went to all hands meetings. So I think it's no secret now that big astronomy project was actually, that I was talking about was actually LSST, now the Roodman Observatory. Although I will tell you that people who saw that talk, and given that I didn't name the big astronomy project, people came up to me and said, "Oh, were you talking about my project?" And I was like, actually, I wasn't talking about your project. So I think this is actually a ubiquitous issue across, or at least was a ubiquitous issue across many different projects. But why I'm encouraged is that I had concluded in that talk that we really needed something like research inclusion, not just education and public outreach, which is a great thing to do, but we needed to involve inclusion in all of the work that we do, all of the scientific work, all of the technical work that we do. And so research inclusion needed to be part of all of what the project was doing, not just a side hustle that when it doesn't have enough funding just happens to disappear. And I'm really encouraged that what I see in the Roodman Observatory and over these other and over the years is that we're starting to value this idea of research inclusion as part of how we assess the scientific merit of the project. How are we being inclusive? How are we trying to get equity for folks to be involved in our community? And so I want to tell you a little bit about what I mean by research inclusion. So I am not at a small or underserved institution, and so I don't know what I don't know. And so I reached out to some of my colleagues who are at these kinds of institutions, and they wrote back to me and I said, why aren't you involved in these big astronomy projects? What are the barriers that you're seeing? And they wrote back to me with a number of comments, and I boiled them down to basically 4 areas. One of them was that they didn't see opportunities for scientific networking and collaboration building because they were at small colleges, they had high teaching loads, there just weren't the opportunities there for them. They couldn't go to some of the bigger meetings or some of the more specialized meetings. They mentioned technical infrastructure that they needed because they didn't have the resources available at their institutions. And they mentioned that they needed opportunities to be trained on those new tools, those new platforms, those new ways of doing science. And they needed that training not just for their students, but also for themselves as professors who, you know, sort of weren't, had done their studies before all these tools became available. And they also told me that there weren't a lot of policies in place, and that's why it's number one. There weren't a lot of policies in place or procedures that really supported mutually beneficial partnerships. There weren't a lot of reasons for folks at large R1 institutions to partner with folks at smaller institutions to help them move into these kinds of collaborations. And so, being someone who's kind of a policy wonk at this point, I started thinking about what I could do. And so in my position as the head of the Research Inclusion Initiative for USELTP, we started talking about what are the policies we could put in place to make it so that folks who get time on the telescopes actually have to think about how they're going to be inclusive in those collaborations and how they might try to help support folks at smaller institutions. And so we came up with this idea of requiring research inclusion plans within proposals. The first thing I thought was, well, if you ask astronomers to do something, they're going to immediately say, I don't know how to do that, so what do you want me to do? So the idea was to prepare the community for these inclusion plans by building a toolkit of collaborative practice that would be a guide. And we would seed that guide with some of the things that are already going on in the community and enhance it through the understanding of how the efficacy of some of these practices, including some of the metrics, and we would provide recommendations for how to assess inclusion plans, and for the review of how well these inclusion plans are working after people actually got time on the telescopes and started implementing these plans. And as I started shopping this around and telling folks in other places about this idea, NASA decided, hey, we could just do this. We could just do this now. And at the time, I actually had already hired a sociologist, Dr. Tim Sacco, to help me write this toolkit of inclusive practice. And I was excited because I'm like, look, NASA's going to do the experiment for us. We're going to see what people do if you give them no information. If you don't have a toolkit available for them to use, what kind of plans do they put in place? And so we were able to work with NASA actually to take the data from that first call and analyze it and look at it. And we wrote up a report that you can find in the Bulletin of the American Astronomical Society. And I just want to give you a few highlights of that report. The first is that you can see over here on the right, that graph. And the blue is the distribution of grades from the 119 proposals that were submitted. And what you can see is they peak pretty strongly around good fair, maybe a little off into the good, but there's a really strong tail towards poor and a very weak tail towards excellent. And so it's clear that there was a need in the community for our toolkit that we were starting to write. I want to give you a couple other brief findings from that paper, but I encourage you to go read it. And the first one is that the inclusion of a good practice did not necessarily lead to a good grade. And I want to, as an example, I'll say that many of the proposals actually had codes of conduct. We have codes of conduct for Roodman and for all of the science collaborations. But just having a code of conduct did not actually mean that it was implemented well. And so how you implement something really matters. You can see the distribution in orange of the grades for folks who had put that will have a code of conduct in our plan. And you can see that it just mimics the same trend as the overall trend. So when you think about a code of conduct, you need to put it in place. It's a policy. You need to review it. And if it's not working, or if it has holes, we need to revise it. The next finding was that there were a number of themes that people put into their plans. However, a lot of people implemented some of the easier things, and we might have expected that, but the things that might be the most impactful for leveraging diversity, equity, and inclusion were not always in people's plans. And we show that by showing a table of the different themes that people put into those plans. And those themes were, a lot of people did credentialing. Credentialing just means that you say that I have expertise, I've done this before, or that my department has done it before. A lot of people said it wasn't clear that they had actually done anything, or that my university has done it before. So how impactful those are, it was not necessarily clear. It depends on how people wrote them up. But codes of conduct were ubiquitous, and even normal mentoring was something that people put in. All good things, all great things to do, but not necessarily the most impactful depending on how you described what you were doing. Things like substantial evaluation of the environment in your collaboration, or things like cross-institutional partnerships, or leveraging those cross-institutional partnerships for diversity, equity, and inclusion were were very rarely in people's plans. And so I just want to give you a sense of this evaluation, how evaluation fared as a component of people's plans, where you can see here in orange that the plans that included a substantial evaluation component actually on average did better than some of the other plans. So thinking about and trying to understand how your inclusion plan is working, and also what you can do to make it better, was something that was valued by the reviewers. And I want to point out, as far as cross-institutional partnerships, that as part of Roodman, there's Louise Edwards, who's here, gave a talk, and I've been involved with her program, where she has a pair program where she has leveraged her position as a DPO delegate in order to build an innovative partnership across primarily undergraduate institutions, and have the professors at those institutions, who maybe are not doing the same science, but are trying to use the Roodman Science platform to get together, to help each other, to work on how they can best use the platform when the data becomes available. They're working with groups of students to do that, and I think the building of these kinds of networks across these different communities is really important, and Roodman's been able to help by providing delegate status to her partners in that program. I also wanted to point out something that the Transients and Variable Stars collaboration, along with Milky Way, Stars, Milky Way, and Local Volume, and the Solar System collaborations have done in finding grant money through Heising-Simons to give out Kickstarter grants to folks. And you can find more information about those about what their program, I think it's over now, or maybe it's gonna, yeah, it's over now. But these are the kinds of things that, if they're in an inclusion plan, really make for a good inclusion plan. And so you can see more about what they did at that link above, but I also wanted to point out Nino Cucchiara's project to really help and support folks at smaller institutions to be involved in Roodman again, by partnering with folks who are already involved in Roodman. And so there are at least two talks. There's a talk by Nino, and also a talk by two of the folks in his program who are at Hispanically Hispanic serving institutions in Texas. So check those out if you want examples of good things to do for inclusion plans. The third item that I want to point out is that the evaluation of those plans was actually done by DEI expert panels. And so the grades that you saw there were these panels made up of people who understand, sociologists, but also astronomers who have been working in these areas for a while. However, the science experts were also asked to review those plans. And unfortunately, they weren't asked to grade it, so we couldn't do a one-to-one matching of the grade, where the grades fell for the reviewers. But since Tim is a sociologist, he understands words, and he was able to look at the descriptions that people put in and do some comparison. And so what we found was that the science experts, they didn't identify the same critiques on the inclusion plans as the DEI experts, but they also didn't sort of go, oh, this is fine, no worries about it, right? So and so this plot actually shows for cross-institutional, for the plans that had cross-institutional partnerships, some whether the DEI panel or the science panel found a weakness or a strength or didn't mention anything at all. And we're encouraged by this because we think, that the science expert panels are not that bad at it, but perhaps there's opportunity for training and a better understanding of what makes a good inclusion plan. And that's something that we wanted our toolkit to actually help with. I would argue that, in fact, at Roodman, and the Roodman ecosystem, we have been looking at trying to improve a scientist's understanding of what makes for a good inclusive collaboration. And an example of this is the From Data to Software to Science with Roodman Observatory LSST workshop that happened in New York. And whereas the primary goal of that workshop was about identifying use cases for LSST and early science data and how we could, what kinds of computational and technical challenges we needed to identify now in order to work on the data. That whole meeting also had a section of the meeting that was devoted to understanding inclusive collaboration and practice. And so in the document that there's a link to here, that is the whole white paper about the entire meeting, the information about inclusive collaborations is captured, and also scenarios and use cases for inclusive use cases around scenarios that might lead to people thinking about what makes a good inclusive collaboration. So topics like institutional pressures for different people at different institutions, allocation of credit, those kinds of topics. And so we are starting to do the work of informing ourselves and giving ourselves some training on what kinds of things are good to have in a collaboration and how do we implement them in the best way to make our field more equitable, more diverse, more inclusive, more accessible. And so I just want to finish off by saying that Tim and I have built this toolkit of collaborative practice from the findings of our report. Originally, we thought we had 3 years, but now we find that this toolkit is really needed now. So we put out a first version of the toolkit based on the findings of the report to select different themes that we would do first, and from some of the seeded from some of the activities that we see going on at Roodman and in other parts of the community. And this is not just a list of papers, sociology, social science papers, and websites, which I think has been done in the past, but this is really an inventory of resources, and they're resources that have been curated and organized. We pulled out some of the best practices, and we put it in a tool where you can filter on maybe themes that you're particularly interested in. And so this is our this is the web page for our toolkit. The QR code is there to go to a page that'll lead you to, that talks about research inclusion, then lead you to our toolkit. And I really encourage you to have a look. This is the first version. We have another version that we're hoping to get out before Tim leaves for his Catalyst Fellowship at the end of the month. But you can see here that there are, we have a theme and its description, and then we have some best practices. The best practices we've arranged as the minimum thing that you should be doing is at the top, and then some other practices that are kind of bells and whistles that will depend on whether how or whether you implement them might depend on your resources or your availability, the size of your collaboration. So we wouldn't expect you to do all of them. We expect you to tailor what's in the toolkit to your specific need. And so in summary, I just want to say that I think we really are ready to move into a place where we are seeing a change in in astronomy and astrophysics around being more inclusive, being more diverse, being more equitable, and having better accessibility, both to the data, but also to advisory accessibility and talking with those who are experiencing the biases and the barriers to being involved. I'm seeing that the leadership is ready to help us do that by providing incentives, but we're not there yet. We are not there yet. And we need to keep vigilant on really promoting these ideas within our community so that in the next meeting, we see more folks from smaller universities, we see more folks of color represented amongst the participants in this room. And so with that, I'll just say that we really must continue the support of not only the scientific excellence that we've seen here all week, but also those who animate it. And thanks all. I'm happy to take any questions. And as you're coming up for questions, I want to point out that we have a feedback button on our webpage, and we really would love people who, even just if you're just looking at the webpage and you have some feedback or some suggestions or you'd like to see other topics represented, please send us some feedback on the toolkit. Thanks.
Hi, thanks for the nice talk. I'm Chris Walter. On one of your early slides, you talked about programs that had pros and cons, and you mentioned bridge programs. Mm-hmm. And I was just wondering if you could tell us some of your thoughts about bridge programs and how they might be better. And also, I'm interested in knowing your thoughts about when we're trying to help students who are thinking about going to these students, what sort of things should we think about when we're trying to help and mentor them? Thanks.
Yeah, thanks for that question. So bridge programs, sort of are conceived as a way to have students who maybe are thinking about but not ready for getting a PhD in astronomy or astrophysics. It depends on where your bridge program is centered. It could be from, you could be bridging, I guess, from high school to undergraduate or undergraduate to graduate school. But the idea is to help those students maybe think about or identify how they might want to move into the next step. The devil is really in the details as far as bridge programs go. And some of those bridge programs really have a sort of fix the student mentality, right? Again, ability is everywhere. Access is not always everywhere. Just because a student hasn't taken calculus or hasn't taken the all of the physics does not mean that they can't do it, but some of the bridge programs treat like, oh, there's this deficit in the students and we gotta fix that. And I think that does more harm than good. I think what we wanna do is treat students like, oh, you've come in here, we see that you have not had an opportunity to have XYZ class. Let's make sure that, you know, you're working at the level that we need you to work so that you can do the work. And so I really think that not having this deficit-minded approach to a bridge program is what makes it successful for the students or not successful for the students. And I'm happy to talk more about it because there's a lot of nuance.
Go there.
Okay, Fed.
Thank you, Dara. This was amazing. I wanted to go back to the program that you mentioned that Nino Cucchiara ran through the Kickstarter grants. And I want to reveal, because I was involved in this program, that we had a really hard time, Nino had a really hard time finding the mentors of LSST inside of Roodman that would partner with the individuals that were selected. And so on one end, not a question, it's a call to everybody to like step up to the responsibility. But also it is a question because mentoring is hard to begin with. Culturally sensitive mentoring is harder and it may be daunting. So how can we help the people in the community feel like getting involved is a little bit easier?
Yeah, so during one of the breakouts yesterday, we talked a little bit about that, the differences between folks who are at R1s and who are at smaller institutions, right? I mean, the institutions cited here that are Hispanic serving institutions are all relatively small. And so this is where this idea of understanding the scenarios, one of the big things that I think is really important when you're doing any kind of collaboration between folks at different institutions, especially if one is, you know, an R1 and one is maybe a minority serving institution, is to have the hard conversations up front, to recognize and understand what people's positions are, like what is their institution gonna value, what is it not gonna value, how much time really can you spend on this, what level are your students at, and put a collaboration in place that recognizes that this might be an asymmetrical partnership as far as expectations of what can and can't happen, right? People at R1s are used to some pace that, you know, people at smaller schools are used to a different pace, right? And so if we're gonna have these partnerships that really work, we need to up front talk about what are the things that we can do together, what are the things where, yeah, this isn't, you know, critical to the paper or whatever the project, so we're gonna let you work on it on your time scale or things like that. But I think we have to have those conversations before it just becomes a crisis and somebody's like, oh, they're not doing what we expected them to do. Well, did you talk to them about what they expected, you know, this was gonna be as well? So, yeah, that's my comment. Another question?
Yeah, I'm going to invite Meg Schwam to unmute and ask her question.
Hi, Meg.
Hi, thanks for this great talk. I wanted to ask about your thoughts about sort of Roodman's ecosystem has sort of changed the way astronomers interact with the facility, and that there's a lot of requests for feedback. And serving on panels for not a week or a day, it's like months. And I'm wondering, again, thinking about that participation and people having time to be able to do things, as we talked about, having difficulty finding people to be mentors for some of the programs that were discussed. How do we make sure that we're allowing people to be able to step up to the plate, to be able to participate in these discussions and, you know, in these opportunities to give feedback and serve on committees that are required now, thinking about Roodman and probably in the next generation of telescopes and surveys, when it's a lot of time and effort. And right now we're kind of being assumed that it's the check mark you add to your CV, right, to serve on this panel But that's not everyone's ability to do that, right? Especially people with higher teaching loads or from non-traditional backgrounds. And so how do we make that easier to broaden participation? I'm just wondering your thoughts on that, because it doesn't seem like a necessarily easy fix. And there's not grant money to go around to pay every member to be on every committee.
Yeah, there's definitely not an easy fix, and I would say that's where the cultural change comes into place. People need to recognize and understand that these kinds of partnerships, these kinds of ways of broadening the participation over a wide group of people, those are part of the scientific merit of what we're doing. I'm going to say that again because I truly believe it. It is not only the science that we're doing, it is the ways that we are involving all of the communities in that scientific effort and making it broadly available and making opportunity broadly available to a wide group of people. And I think only when we actually internalize that as something that's part of our culture, will it be easier for folks to sit on some of these panels and do some of this work without people saying, well, you didn't put out a paper, you didn't put out X number of papers like in this time period. You were busy wasting your time on a panel to make things more inclusive. I think that's a cultural change we have to see, and I hope we get there, and I think that we're ready to get there. I also, you had another point about, I don't pretend to think that everybody is going to feel like this is for them, but I do think that the people who are engaged and are interested, I want to make it so that they get credit for the work that they do. And I want to make it so that people who feel like this isn't for them, they recognize how much work it is and how important it is. And the fact that the money for building these large telescopes and doing this science comes from people who are not engaged in the science, right? And we don't just, we want to make them feel like they have a stake in this because, you know, because the whole community can be involved in it. It can be something that everybody can be involved in. So I think recognizing that there are some of us out there who are doing things for the wider audience is an important thing. I have a lot of opinions. I'm sorry if I didn't answer your question, Meg, but... Okay, well, thank you very much.
Okay. One more time, thank you, Aaron and Dara, for a great morning session. And I just want to take this really quick opportunity before you run off to break. As you heard from Bob on Tuesday, the operations team is taking over PCW and running with it. And I just want to extend my thanks to them, particularly to Rampal and Melissa for all the work they're doing. The IT team. All the admins, the whole committee that's making this happen. We're still going to be around, unfortunately, for another year or two. But I'm really looking forward to see how the community runs with this great facility. So I just wanted to take the opportunity to thank you all for setting it up this year and to continuing on with it. Coffee break, right on time.